Hello everybody. I would like with this video to cover just a couple of things that we didn't manage to cover yesterday at the lecture, something actually extremely brief and basically related to light emission and a few definitions related to anything related to light effectively. So this will be quite brief, and then I would like, as I mentioned yesterday at the lecture, I would like to show you some very nice applications of the concept we went through yesterday, about generation and recombination of carriers, continuity equation, and so on. So I think these very nice applications will allow you to see a bit more applied, these concepts that are very important in general for anything that relates to semiconductor behavior. So have a look and have fun, and I'll see you next time. See you later. So the first, the thing that yesterday I didn't have really the time to conclude was related to light emission. So we did have a look at light absorption during the lecture, and effectively light emission is just the reverse of the processes we've seen yesterday. So if you remember, just to summarize, yesterday what we did was just a moment. So what we did yesterday, we had a look at the processes that are involved in light emission, light absorption, both in direct semiconductors and both in direct semiconductors. And you remember that we saw this diagram here with the transition, the vertical transition, which is allowed by photons here, and then we saw also the case for exactly the same transition, band-to-band transition, from the valence band to the conduction band for indirect semiconductor this time, and we realized that here we need to include also another particle that was the phonon for this transition to be allowed effectively. And so we wrote also the conservation laws, if you remember, for energy and momentum, and so on and so forth. And so at the end of the story, we realized that we said that indirect semiconductors are bad light absorbers as compared to direct semiconductors, because they have to find the right phonon for the transition to be allowed. So for the absorption of the photon to take place. And we also realized yesterday that in the end, from all the things we've said, we realized that on the EK diagram, photons allow for movements, let's say, that are in the vertical direction, while phonons on the horizontal direction. Yes, this is really, in a very briefly what the key points that we saw yesterday when we were discussing light absorption. So let us have a look now at light emission. So once the electron and hole pairs are created, they tend, first of all, to thermalize. That is, if you go back to these to the energy diagrams, to the energy band diagrams we drew here, for example. So once the electron is promoted into this state, they tend to lose through scattering this energy and tend to move toward the bottom of the conduction band. So that's what I mean by thermalize. The same happens to the hole that is left behind. Also the hole tend to thermalize and to move toward the top of the valence band. So this is one thing to always keep in mind. Once we have a promoted carrier into the conduction band, and so also we have a hole left behind, they always tend to, sorry, you can't see this sentence, they always tend to thermalize toward the bottom or top of the conduction band or valence band. And then from that position that is now closer to the conduction band edge and the valence band edge, they then recombine. So at this point we know that, as we've said yesterday in our introduction to generation and recombination, we know that recombination then will be radiative, or could also be non-radiative, as we explained. And radiative recombination, as we have seen, is the one that comes from a direct recombination process, so a band-to-band recombination, as we've described yesterday. So the process we've described yesterday, if you remember, were related to direct recombination. And this will result in the emission of a photon of energy close or just a little bit above the band gap energy of the semiconductor. So that is, in a nutshell, how light emission takes place. It is the specific processes differ, as we've seen during light absorption yesterday. The specific process depends on the fact that the semiconductor may be direct or indirect. So the processes are exactly the reverse of what we've seen yesterday, and everything we've said holds exactly in the same way. So the final result of what we are going to say effectively now about light emission is that using borrowing, let's say, the results that we've got yesterday for the light absorption case, we can immediately say that indirect semiconductors are definitely bad light emitters as compared to direct semiconductors. And this is because, again, the indirect semiconductors require the presence of a phonon for the transition to happen. More specifically, we can have a look at these diagrams that are, as you can see, they are exactly the same as those that we've seen yesterday. Simply, we have reversed the transition. Now is opposite. So in the case of direct semiconductors, light emission from during a direct recombination process is represented by this diagram, where we have our electron is up here and wants to go to recombine with the hole that is down here. And so the transition is this one here, represented by this arrow. So the conservation laws at play here are, before the transition, the energy of the system is EB, which must be equal to the energy of the system, so the electron when it is down here, which is EA, plus the energy of the photon emitted. It's clear that the energy of this photon will always be bigger or equal than EG. And on top of that, considering that the momentum of the photon, as we discussed yesterday, is effectively negligible as compared to the momentum of electrons, we can say that in this transition, the conservation momentum means that KB must be equal to Ka, and so we have this vertical transition, as we've already learned from yesterday's lecture. And overall, the transition, the probability for a radiative transition from B to A could be written in this case as this thing. So F, remember, is the Fermi distribution function. So F EB, so this is the probability that an electron is in state B with energy EB, time the probability that in the state with energy EA there is no electron. So this means 1 minus FEA. So this is for the light emission in direct semiconductors. For indirect semiconductors, we have again something similar to yesterday's, only obviously the transition now is reversed. We want to go, our electron, let's say, is here, and it wants to recombine with a hole that is here, so the transition is this one here. And so we need to involve the phonon that will provide the momentum required equal to the mismatch momentum between the KB and KA. And so the conservation laws say that the energy in EB must be equal to EA plus the energy of the photon. We are not including the energy of the photon that must be emitted because we know that is anyway negligible, very small. And then we have K of the momentum before the transition, which is KB, must be equal to the momentum of the photon plus Ka. And so overall, we can see that the conservation laws, the total probability for a transition, a radiative transition in this indirect semiconductor can be written like that, as very, very much similar to what we did yesterday. So based on all this, we can now try to understand, as we did yesterday. You remember yesterday we looked at how is the absorption spectrum in semiconductors, and if you remember, we had a look at the absorption coefficient as a function of the energy of the photons that hit the semiconductor, that are absorbed by the semiconductor. So here we would like to do something similar, and to understand how the emission spectrum now looks like, we can get some help from something we've already done last week, actually. So if you remember, last week we realized that in a semiconductor the electrons and the holes have a very peculiar distribution in energy, and this is represented by these curves that I've drawn here. You remember these kind of shapes. So if this is the energy axis here, and this is the EC, and this is EV, the conduction band energy, and the the valence band energy. So we know that the distribution in energy of electrons, for example, is this shape here. If you remember, this comes from the fact that the product between the Fermi energy distribution and the density of state. So you can go back and have a look how we found out about this shape. And so the emission process, the light emission, effectively implies that we have a state here. One electron is occupying this state and wants to effectively recombine with a hole that is down here. So obviously this function here is the function that is telling us how these electrons are distributed, and where there are, obviously, it's telling us how many also are these electrons. So at this energy, there is a certain number of electrons. At this energy, there are more. There are more up to here. This is the maximum, and then there are less down here. So you probably are already guessing that where I'm going is that the emission spectrum of a semiconductor is effectively kind of related to this shape, and actually is exactly the same. So if we were to plot the intensity of the light emitted by during radiative recombination of a semiconductor, regardless now whether it is direct semiconductor or indirect, the energy distribution of this this light emitted is exactly following the distribution of the electrons that we've seen above. Actually, if we do the full analysis, we realize that this shape is has this proportional to this quantity here. So it's proportional to E minus EG to the 1/2, so this square root of this quantity, and this, if you remember, is this part here of this distribution was proportional to E minus EC to the square root of E minus EC. So and similarly, this part of the distribution was proportional to EV minus E, the square root of EV minus E. So this term here is responsible for this initial part, and then we have an exponential term that is decreasing, and this is this term here, which also is related to the Boltzmann distribution and so on and so forth. And so we can clearly see that this is we should not be surprised by the shape of this emission spectrum of light coming out of a semiconductor during a radiative recombination, because this is effectively imprinted into the fabric of the semiconductor by these distributions. Okay, so it actually comes down to where the electrons are and where the holes are, obviously. Now, if we do the maths here, we can realize that the peak in the intensity of this distribution, of this spectrum, is at Eg plus kT over 2. Or remember, the kT is very small. It's 26 millieV at room temperature. So we realize that this spectrum is very, very sharp in energy. So, for example, silicon has an Eg of 1.1 eV. So this quantity is very, very close to 1.1 eV. KT over 2 is just 13 millieV at room temperature. So, and the full width half maximum is rough. So the width of this spectrum is also very, very small. Is around 1.8 kT. So, because the width and the peak position are the width is so small, and also the peak position is extremely close to Eg, we could, in our mind, really approximate things and say that it would be completely fine to say that effectively the spectrum of the photons emitted from the direct recombination process in semiconductors is effectively distribution like this one around the G effectively, with a full width of maximum of 2 kT. So this would be absolutely a fine approximation. And to conclude this part regarding light emission, we have said that recombination can be radiative in the case of direct recombination, but can be also non-radiative. So if we call tau the time required for electron and hole pairs in general to recombine, regardless of the process, we can easily understand that, as we did, we used a similar concept when we were talking about mobility, when we introduced drift and diffusion and so on and so forth. We can easily understand that the probability of a transition from B to A is proportional to 1 over tau, if tau is the time required in general on average for electron hole pairs to recombine. This is obviously because if tau is large, this means that there is a very small probability for a transition from B to A. And so that's why we say that this must be proportional to 1 over tau. Now, since we can easily realize that the total probability for a transition from B to A can be split into probability of having a transition that is radiative plus the probability of having a transition that is non-radiative, we can easily guess or realize the way that the lifetime of electron and hole pairs, so the recombination time, if you like, adds up. So because these probabilities are added, and we said that each probability will be proportional to the corresponding 1 over tau. So we can say that the total 1 over tau is equal to 1 over tau radiative plus 1 over tau non-radiative. So we are effectively saying here that radiative processes have a specific lifetime. The electron hole pairs have a specific lifetime, those that undergo then the radiative recombination, while those that go through a different path obviously have a different lifetime. And we conclude this part by defining the so-called internal quantum efficiency of a semiconductor, which is indicated by the Greek letter eta. And this is defined as the probability of a radiative decay divided by the total probability of decay. So effectively is defined by W rad over W, which based on our above definitions is effectively the ratio between the total time for recombination, the lifetime of electron and holes pairs, divided by the lifetime for a radiative recombination. So this concludes effectively what I wanted to tell you yesterday. This was the only bit that was left. There is this nice slide also that I've prepared for you, which summarizes kind of all the definitions related to light that you could imagine. I've tried to be as exhaustive as I could. So, for example, consider a beam of monochromatic photons. Okay, so we have our photons. Imagine they are moving. The beam is effectively identified as a cylinder full of photons that are, moving in this direction. And there are, let's say, n photons, for example, each of energy hν. That are the A, let's say, is the cross section of this beam, the area. We've already defined yesterday when we were discussing, if I remember well, generation processes, and specifically generation by light. We introduced the number n, capital, which we said was the number of photons that hit the unit surface per unit second. And we also said that, look, this is effectively, we will demonstrate that this is what we call photon flux. And that's what I will show you now in a moment. So going back to the definition. So regarding the photons, we say that the energy of the photon is hν, and using the relation between lambda and n and c, which is the speed of light, we can write this also as hc over lambda. And remember this nice relation that allow you to go from lambda in micrometers to energy of the photons in eV. And the momentum of the photons, this is a small p, ph, just not to confuse this with the power of the beam that we will see later. So this is a small p, equal to h bar k. Remember, h bar is h over 2p. H is the Planck's constant, k is the wave number, wave vector, where k is 2p over lambda, and so p, the momentum of the photon, can also be written as h over lambda, where h, remember, is this number here. So this is just to remind you about the photons, their key quantities, and let's go to the definitions regarding the beam now. So we define photon fluence, we can indicate it with F, pH, the number of photons per unit area, so n over A, and is measured obviously in 1 over meter squared. The photon flux defined by, which is the quantity that we said is equal to the n we introduced yesterday, which is the number of photons that falling over a certain area A in a certain time t. So based on this definition, this is also the photon fluence divided by the time. And so the units are 1 over meter square per second. And correspondingly, we can define the energy fluence, Fe, which is based on the previous definitions, the energy of the photons time the photon fluence. And so it's simply the units joules per meter square. This is also what you may see, sometimes you may see called as energy density. And then we have also the energy flux, so phi E, which is effectively what we call also intensity of the beam. We indicate it with I also, and this is effectively the photon fluence time the energy of the photons. And so the units are joules per square meter per second, or watts per meter square. Or the energy flux is also often called intensity of the beam, or also power density, or also irradiance. Okay, so try to become familiar with these names. And finally, the power of the beam, which we will indicate with the P capital, pH, is simply the energy flux time the area where this beam is falling onto, and so effectively corresponds to this based on the definitions we just made, and is measured obviously in watts. This is also often called radiant flux. At this point, just for you to know, we should also remember that so here these definitions are very meaningful in general, but also especially in the case of a beam. So a monochromatic, generally a monochromatic in our case, monochromatic beam, monochromatic ensemble of photons traveling all in the same direction, as I've shown in this diagram here. Obviously, what do we do when the source is a point source? So in this case, when we are dealing with the point sources, we have to change a little bit, enrich a little bit our definitions, and in defining quantities and units, we consider both the area where the photons are falling onto, but also is useful to use also the solid angle. Remember, the solid angle is measured in steradians, and remember that 4 pi is the full solid angle. And remember also that in this situation, when we have a point source, the area A on which the photons are falling to is proportional to r squared, the radius of the distance effectively between the point source and the point in space we are interested in. So this is also something to consider. So the area increases with the distance squared. And so here I will show you now some units or quantities that are often used. You may come across these things. This is just for your curiosity mainly. The quantities that are used for point sources, and also the corresponding quantities that are used that are related, also take into account maybe the human perception of light. So the physical quantities are called radiometric quantities, those that are based on radiometric quantities, but also take into account the human perception of light, the fact that the human eye has a certain sensitivity at some wavelengths rather than others. These are called photometric. Okay, so I'll put them side by side so that we can understand better. So as you can see, the photometric quantities are weighted using luminosity function of the human eye. I will show you this luminosity function later. It's just at the bottom of this slide. So the radiometric quantities in the case of point sources that are meaningful to consider are these. So the first one is the radiant flux. This is effectively the power. We've encountered this name before here up here. I've already used this name, if you can see. Radiant flux is the power of the source. The corresponding photometric quantity is luminous flux and is measured in lumens. We will see what the lumen is. Then we have the irradiance. The irradiance is the intensity, what we called previously intensity also. If you see, we've introduced the irradiance as well here. So irradiance is how many watts per square meter. And the corresponding photometric quantity is the illuminance, and is measured in lux, which is a lumen per square meter. And then we have the radiant intensity. So this is watts per steradian. Okay, so how many watts per unit solid angle the source is emitting. And the corresponding photometric quantity is the luminous intensity, which is measured in candela, which is a lumen per steradiant. And finally, the radiance. The radiance is watts per steradian per square meter. So as you can see, this is obtained from the radiant intensity dividing by the area it is falling to, this specific radiant intensity per unit area effectively. And the corresponding photometric quantity is the luminance, which is measured in candela per square meter. As you can see, it's not by chance that I've chosen this sequence here, because the next quantity is always obtained as from the previous one. So irradiance is obtained from the radiant flux over per unit area. The radiant intensity is obtained from the irradiance, no, the radiant intensity is not. So the radiant intensity is watt per steradian, and the radiance is obtained from the radiant intensity per unit area. And the same story obviously holds on this side. So as you can see here, we are using new, now for the photometric quantities, we are using new special units, which is the lumen, the lux, and the candela, which are defined down here. The candela is this is actually a unit defined in the international system, as weird as it can sound, and it is defined at lambda equal 555 nanometers, because this is where the luminous function that I told you represents, the response of the human eye is equal to 1. And so at this point we can find the correspondence between candela and watts effectively. So one candela corresponds to 1 over 683 watts per steradian. The lumen, which was the unit of, remember the candela was the unit of luminous intensity. So the candela is how the human eyes perceive light intensity, if you like. The lumen, which is the unit of luminous flux. So the lumen, also defined at lambda equal 555, 1 lumen is equal to 1 over 683 watts. So the reason we pick this is effectively what I mean with what I said previously, is that lambda equal 555 is the only wavelength at which we can find a direct correspondence between the radiometric quantities and the photometric ones. So 1 lumen is equal to 1 over 683 watts, and finally the lux, which is the unit of illuminance, and the lux is 1 over 683 watts per square meter. So, and to conclude, the luminosity function I mentioned previously, which represents the sensitivity of the human eye to electromagnetic radiation of different wavelengths in the visible, is effectively this function here. So as you can see, it's at lambda equal 555 that this function is 1. Okay, so while obviously the sensitivity is smaller than 1 at wavelengths that are different from that. Okay, so this concludes effectively what I wanted to tell you, and at this point, if you're not interested in watching the applications that I'm going to show you feel free to stop the video here. But I'm going to now show you, I think, 3 applications based on what we discussed yesterday regarding generation and recombination and continuity equation and so on and so forth. So the first example I wanted to show you is effectively related to the fundamental equations we saw yesterday when we introduced the generation recombination, and it is effectively this example here. So the light effect on carrier density in a low injection situation. So we are assuming here that we have a thin piece of N semiconductor, direct imagine it is, which is illuminated uniformly. So illuminated uniformly by a light source generating a certain number GL of electron and hole pairs per unit time. Remember, GL is the generation rate. So uniformly means that GL is the same for us throughout the piece of semiconductor. That's why we said that we are assuming that it's a thin piece of semiconductor, so that we can kind of see this process happening. Okay, so GL is the same everywhere throughout my semiconductor, as shown in this nice picture. So at steady state and under illumination conditions, from the equations we've seen yesterday on when we were introducing recombination. So we saw, you remember, that we can write that dPn dt is equal to GL minus U. At steady state, dPn over dt must be 0. So this means that we have at steady state in this example 0 equal this, and so because U is equal to this quantity here, we can and we know GL, we can easily realize that when the light is on, Pn is equal to this. Pn0 is the value of Pn at thermodynamic equilibrium, and so we can see that this is the added amount of carriers, of minority carriers, that have been generated by light. So delta N or delta P is GL tau P. So that's quite interesting here, how, first of all, how GL effectively directly relates to the number of electron and hole pairs being generated. Now, let us imagine now that at t equals 0, we switch off the light. So if we switch off the light at that very moment, from that moment onward, the equation I need to solve is this one here, where GL is gone now. And so the equation becomes effectively this, and we end up, if we order better the terms, with this equation here. This is a non-homogeneous first order differential equation, which we can solve. We've solved before this type of equations, so the solution can be written like this. And if we impose we impose, for example, that Pn at t equals 0 must be equal to Pn when the light was on, which was this value. So when t is equal 0, Pn must be equal to this first condition, and so this drives to this condition here. And while we can see that when t goes to plus infinite here, this term disappears, and so Pn infinity must be equal to B, but this must be also equal to Pn0 effectively, because when we switch off the light, the semiconductor will eventually go to the thermodynamic equilibrium value. And so the other condition is this one here, for example. And so from this system equation, we find out that A's must be that. And so the final solution when the light goes off is this one here. Oh, note that when t goes to infinite, obviously we recover the thermodynamic equilibrium. Okay, that's quite nice. So we can see this now in a nice plot. That is this one here. It's in your book, actually, one of the references that I've mentioned. So when the light is on, so in this side the light is on, we can see that the density of minority carriers, Pn, is increased because of the generation due to GL. and the amount is tau PGL. Tau P, remember, is the recombination time of for the semiconductor, the lifetime of the minority carrier, sorry. And from the moment we switch off, so here we switch off the light, and so according to this equation, the density of minority carriers falls exponentially and eventually goes down to the thermodynamic value Pn0. Okay, that's very, very nice. So we can see immediately and directly that light can be used to change the amount of minority carriers in my semiconductor, bringing the semiconductor out of equilibrium, and then as you switch off the light, the semiconductor reestablishes equilibrium eventually. Now, at this point, this is all very nice. Let's see how this applies to real life. So, we need to remember that when we defined drift, we also realized, which was here, we realized, if you remember, that when we defined drift, we defined effectively sigma, the conductivity of a semiconductor, or also the resistivity of the semiconductor. And we saw that sigma, the conductivity, is effectively given by this quantity, E time P me of the holes, of the P carriers, plus N time me of the electrons, or me of the N carriers. And so that's what I'm doing here. So I remember that sigma was given by that quantity, me of the electron time N plus me of the holes time P, all multiplied by the elementary charge. So we realize now that when light goes on and off, effectively P in this N-type semiconductor, Pn, goes from the value it has when the light is on to the light it has when the light is off. Here I call Pn infinite the limit value, when the transient is basically over. So Pn when the light is off is Pn0. So here we have the density of minority carriers is changing also quite a lot. Remember, this may be quite large, as we said. So given the low injection condition that we are working on here, as we defined yesterday, so we know that when the light is on, effectively the density of electrons Nn is not really changing too much. So Nn when the light is on is roughly Nn0. But what is changing a lot, as we said yesterday, is actually the density of the P carriers. So Pn0 is obviously much smaller than N0, and is actually Pn that is changing a lot. So this tells us that we can translate what we've just done into conductivity. So what is the conductivity when the light is off? This is the value at infinite when the transient is over. We can write it using the definition as E me of the electron Nn0 plus the corresponding quantity for the P-type carriers. But you know, this quantity at infinite, we said, is generally very small. This is an N-type semiconductor, so Pn0, this quantity here is Pn0 effectively. And so this is very small, so we can effectively neglect that. On the other hand, sigma, when the light is on, is this one here. Okay, we need now the density of the P carriers is very important now, because it can become quite important. It's much bigger now when the light is on. So this means that sigma, we can actually vary sigma, because the contribution of the P carriers is either negligible or here very important. So we see that sigma when the light is on is definitely bigger, because this quantity is obviously positive, than sigma when the light is off. So effectively we have a light sensitive conductor here that can change the conductivity depending whether the light is on or off. So this is effectively a photoconductor. With a semiconductor we can do a photoconductor. And we can translate conductivities into resistances of a real piece of conductor, of semiconductor, recalling that the resistance is related to conductivity and the geometrical size of the semiconductor through this simple formula. Okay, 1 over sigma is the resistivity. Remember, so R is rho times D over A. So I've replaced rho with 1 over sigma. So the resistance when the light of the semiconductor, when the light is off, when this transient is completely over, is 1 over sigma L of infinite times D over A. When the resistance instead is on, so when the resistance when the light is on is 1 over sigma L on times D over A. And based on what we've said about the relation between two sigmas, we can conclude from this that the resistance of the semiconductor when the light is on is smaller than the resistance of the semiconductor when the light is off. So the semiconductor is more conductive when the light is on, that's all. And so we can think of a nice setup here to actually measure the lifetime of the minority carriers now, tau p. And the way to do this is to consider this circuit. So we have our piece of semiconductor, which has an unknown resistance, which is variable Rx, the variable because it depends on the light, and in series to a resistor R, and we are measuring the voltage at this point. So this is the voltage divider, if you like. So V measured by this component, this multimeter, if you like, is the voltage divider, so R over Rx plus R2, Rx plus R, times the voltage we are applying. So when the light is on, the resistance Rx of the semiconductor is RL on. But if now at time t equals 0 we switch the light off, well, we know that sigma at this time when the light goes off will be based on what we've done here on the general definition. Sigma is this quantity, so we need to replace n with n and 0 and this with p n l off, which you remember we found here. So I do these substitutions. So when t goes off, sigma is actually this. Now this term here is actually what we called, as you can see, is effectively this quantity, you see, sigma L of infinite. So plus this term that is related now to what the minority carriers are doing, Pn, during L off. So we then from this we can calculate Rx when as soon as when the light now is off, and so this is obviously defined as this quantity. And if we substitute everything in, we have this apparently very complex thing, but is actually when t goes to infinite, this thing goes to Rx L of infinite, okay, which is the when now thermodynamic equilibrium has been re-established throughout the semiconductor. So to make this long story short, what is the resistance of the semiconductor doing in this special experiment? Okay, so here we were thinking, okay, light is on, and so the resistance of the semiconductor is small because it's becoming more conductive with light, and then we switch it off, and there will be a transient, and the resistance of the semiconductor eventually will recover to the value that should be in thermodynamic equilibrium. And this is what we are plotting here. So when the light is on, the resistance is Rx L on, which is small because the semiconductor is more conductive. But as soon as we switch off the light, this has a transient and then eventually recovers the value Rx infinite L off, which is the thermodynamic equilibrium value. And so there is a transient, and this transient has a time constant tau p. So because the resistance has this behavior, and given the fact that the voltage we are measuring is the voltage divider, we realize that in the voltage we will be measuring in the above circuit through this voltmeter, for example, or oscilloscope maybe, has effectively this shape. V will be high when the light is on, because Rx is small. But then as we switch off the light, Rx will start increasing, because the semiconductor becomes less and less conductive. And so this will start falling with a time constant again tau p. And so we can use this a very simple circuit to actually measure the time constant of the lifetime of the minority carriers, which is quite interesting. A very simple measurement to measure something so intimate, let's say, for the semiconductor, the lifetime of the minority carriers. And if instead of having light on continuously, you were to apply a very short pulse of light, so imagine light off, the voltage is down here when the light is off, so the resistance of the semiconductor is RXL off effectively. Then you apply this short pulse, so the voltage goes up because the resistance of the semiconductor drops a lot. So based on the previous voltage divider formula, the voltage will increase, the voltage I measure, and then will then drop again because that was a very short light burst, and so then the light is off again, and so this will do that. So you can also use light bursts. So this is the first example I wanted to show you, which I think is a very nice application of generation and recombination concepts to actually measure something that is important, the lifetime of my minority carriers. And I have here another nice example, which is related to generation via light absorption. So here, if you remember, we had said we had found the Beer-Lambert law. So I wanted to show you a nice example here of this of the Beer-Lambert law, which is this one here. So imagine that the absorption coefficient is 10 to the 5 centimeter to minus 1 for a semiconductor. Obviously, this means that the absorption length is, if you remember, which is the inverse of alpha, 1 over alpha, is 10 to the minus 5 centimeter, which is 0.1 micrometers. So this means that photons can travel on average 0.1 micrometers into this semiconductor before being absorbed. So our piece of semiconductor, let us assume, has a thickness of 1 micrometer, and let us assume that a beam with 10 milliwatts per square centimeter intensity is hitting the surface of this semiconductor. Okay, so effectively I'm referring to this kind of situation here. So let us calculate the intensity of the beam at the other end of the semiconductor and also GL at the two ends, assuming that the energy of the photons are 2 eV. Okay, so I want to find effectively the intensity of the emerging beam, but I want also to find out the generation rate of electron-hole pairs at this surface and at this surface of the semiconductor. So based on the Beer-Lambert law, the intensity of the light at depth d, so basically when the beam emerges, is I times e to the minus alpha times d. And so we put in the numbers. Alpha is 10 to the 5 per centimeter. D is 1 micron, which is 10 to the minus 4 centimeters. And so we get, this very small value. As you can see, the intensity of the beam emerging is very small. Okay. The initial intensity was 10 milliwatts per square centimeter. Now the emerging beam is 4.5 10 to the minus 4 milliwatts per square centimeter. And using also the fact that, as we saw yesterday, GL is a function of X and is related to effectively Ix, the intensity at any point within the semiconductor. We have this thing here. So the initial GL0 is effectively given by this. If I want to find the GL at any other point X within the semiconductor, I need to use also this term then. And so using this, you can find that GL0 is given by 3.1 10 to the 21. These are generation events, so electron-hole pairs per cubic centimeter per second. and GL at a depth D is alpha Ni ID now. We found ID previously, so we can use that value. And so it is 1.4 10 to the 17 per cubic centimeter per second. The last application I wanted to discuss with you is the one related to effectively the use of the continuity equation that we discussed yesterday during the lecture. Sorry. So if you remember, the continuity equations that we discussed for semiconductors are those here. Sorry. And these are related to the minority carriers. So this is for the case of an N-type semiconductor, and this is for a P-type semiconductor. So the continuity equations for their minority carriers. And if you remember, we said that if you use for JP or JN the expressions that we found actually last week, if you remember, J, N, or P is always made of two components, one part due to drift and one part due to diffusion. And for the two type of carriers we have, the two equations are these. So if you put everything together, if you put this expression of J into the continuity equations, then they take this form here. And so this is really the most general expression of the continuity equations. And so we can now think of a nice application here that relates to steady state side injection on one side of a semiconductor. So the idea here is to understand how, once we have a light source that is illuminating one side of the semiconductor, to understand how the carrier density, the minority carrier density, how the minority carrier density decays with distance within the semiconductor. Okay, this is effectively is related to the fact that, as we've said, is related to the continuity equations that we will see in a moment. So let us consider an N-type semiconductor, okay, a direct semiconductor, which is illuminated on one side. Okay, consider this situation here. Let us assume that is infinite, the semiconductor on this side. So if you want to see things a little bit better, we can have a look at this image here. Okay. So we are working under the assumption that the energy of the photons is bigger than the band gap, and so this means that there is absorption. Also, this is the relevant continuity equation that we will consider. Obviously, the minority carriers here are P type, the holes. So we are looking at the continuity equations related to Pn, okay, the density of holes in the N-type semiconductor, which are the minority carriers. And so this is all the terms in this continuity equation. Now, we will do now some simplifying assumptions. The first one, very important, is that effectively the generation of electron and hole pairs takes place at the injecting surface. And then Gp is 0 for any x beyond x equals 0. In other words, what we are saying is that the absorption coefficient for this specific semiconductor at this specific wavelength of the photons we are using is effectively nearly infinite, very large. so that effectively all photons are absorbed at or very near the surface. So all photons are effectively absorbed here. Okay, so G is different from 0 only here, and then becomes 0, effectively. Okay, this is, if we go back to what we were saying when we discussed the generation via light absorption, this is exactly this case here that we discussed as alpha large. Imagine alpha is very, very large, then G is different from 0 effectively only near the surface, and is 0 everywhere else, because the photons are now all been absorbed. So this is what the simplified condition we are assuming here. Okay, so G is different from 0 only at the surface, and then is effectively 0. Let us also assume that the electric field is 0, so there is no external electric field applied. So under this assumption, we immediately can understand that within the semiconductor, this is 0, this term is 0 because there is no electric field, and this is also 0. And so we are effectively left just with this equation. So the continuity equation becomes kind of more simple now. Okay, so this is valid at any x bigger than 0. Now, if we assume that we are at steady state means that enough time has passed and the system has reached equilibrium, whichever is this equilibrium, and so Pn is not changing anymore in time, and so dP dN is 0. Recall that Up, as we've seen, is given by this quantity, and that the diffusion coefficient for holes is this quantity here. So we can rearrange this equation. This term goes away, and so this is now rearranging things. We have a second order linear differential equation which is non-homogeneous. This is a constant. This is the thermal equilibrium minority carrier density. And as you can see here, the variable is Pn. Okay, we name dP time tau p Lp squared, where Lp in a moment we'll see is called the diffusion length. Or the boundary conditions for this equation is that we know that at x equals 0, so at the surface where all the photons are absorbed, the density of holes Pn0 will be very large, because there is a huge amount of generation taking place. That's why I'm writing this. Okay, so it will be Pn0 anyway. Okay, this Pn0 at the very surface. So this is one boundary condition, that Pn at x equals 0 is Pn at 0, whatever that is, something big anyway. And on the other hand, we know also that if we are using an infinite semiconductor, when x goes to infinite, eventually the semiconductor is just at the values of Pn are those of the thermodynamic equilibrium, because we are so far from the injecting surface that no change is really taking place there. So this is also a quite reasonable boundary condition to take. And so under these conditions, we can demonstrate that the solution to this equation, non-homogeneous equation, has this form, and we can find A and B by substitution, by imposing the boundary conditions. And so we can easily demonstrate that the solution has this form here. And Lp, which is the square root of dP tau p, is called diffusion length. If we consider now the case of silicon, L is roughly 1 centimeter for silicon, which is an indirect semiconductor, while for gallium arsenide, L is much smaller, actually 2 orders of magnitude smaller, because gallium arsenide is direct semiconductor. So this is what we call the diffusion length, and so what we are seeing here, this equation that the solution of the differential equation we obtained from the continuity equation, is effectively telling us, and here we go back, sorry, so this is the final solution, that Pn at any point x is given by this equation, which is effectively telling us that within the semiconductor, Pn is going like that, is decreasing exponentially toward Pn0. So it's very large at the surface at x equals 0, because there is all the generation taking place there according to our assumption, and then it falls exponentially, and the characteristic length, since we are talking of lengths here, is the diffusion length, LP. So there is now an interesting additional step we could do to this problem in these very ideal situations that we've described. And this additional step we could do is to say that what would happen if, instead of having a semi-infinite, effectively, semiconductor, the semiconductor has a finite length W. And we assume that effectively any you see, according to the solution we've just got, if we were to consider, this, let's say that this is W, even at this point we still have some excess carriers due to those that are generated there at the very surface. So if one thing we could do is to say, okay, let's cut the semiconductor, take a finite piece of semiconductor, but let's assume that I'm extracting any excess carriers in such a way that at this very end, the semiconductor is still, Pn is still the one that we would expect at thermodynamic equilibrium. So effectively I'm saying that let us assume that I'm extracting carriers from this end of the semiconductor in such a way that here I have Pn0. So effectively what I'm suggesting is, let us change the second boundary condition in our solution, and changing it in such a way that we impose that Pnw is actually Pn0. Now, in this case, the solution becomes a bit more complicated. There is no reason to go through the steps here, but we can demonstrate that it takes this form. So you can see that now the exponential term has disappeared. The exponential term that was here has been replaced by a combination now of actual exponential terms, because it's the hyperbolic sign, which is, if you remember, the hyperbolic sign is defined like that. So never mind now the exact details of this. What is important here to note is that this solution is effectively telling us that the Pn as a function of x is going down like that now. But which is based on the boundary conditions we had, is absolutely what we would have probably expected. But now the interesting thing is that this situation arises because we are working on the assumption that we are extracting the extra carriers at W. You remember, if W on the above situation, W would be here. As you can see, Pn at W in this case is not Pn0. It's just a bit more. So this means that to make this happen, we need to extract from the semiconductor some carriers. So we need to remove some carriers. This means that effectively, in other words, to make this happen, we need to in this situation, we can create some current that would flow in the circuit. We are extracting carriers. So we are creating some current. Imagine this is our piece of semiconductor of length W. We are extracting some carriers. So if this is the side that we are illuminating. How much is this current? Well, the way to find it is to use the diffusion, using the equations for the current density for P carriers. In this case, obviously, there is no electric field, so we can straight away discard the part related to drift. Remember that J, where is it? J, in the case of P-type carriers, is made of two terms. So we can throw this away in this case because this is related to the presence of electric field, and we have no electric field right now in there. So J is simply given by diffusion if there is any J. And so we can use this term to calculate J. And we can calculate J, at this point. At the point where we are emerging from the semiconductor, let's say. So we can calculate Jp at W. So Jp at W means minus E, well, we call this E, dP dPn dx calculated in W. So if we take this Pnx, derive it against x, and then calculate it in W, we can demonstrate that this is the result. So as you can see, there is indeed some current, which is non-zero, and this is a diffusion current. So there is some current that is flowing through the circuit, if you like. This is a circuit that we are effectively considering because of the boundary conditions we have considered in this special example. And what we can see from this special example is that if W becomes smaller, goes down, then Jp grows exponentially up, because as you can see, W appears in the denominator through this hyperbolic sign, and the hyperbolic sign grows exponentially. Is exponentially dependent from the argument. And so if W becomes smaller, this will become exponentially smaller, and so 1 over something that becomes exponentially smaller, it becomes exponentially bigger. And so that's why this current grows, is extremely sensible to how much is W. And what we've just described here, the fact that injecting carriers effectively through, in this case through light, but injecting carriers here, we can generate some current on this side, is exactly the principle which is at the heart of the current amplification in the BJT, which we will see in a few weeks. So I thought this was kind of a nice example to think about just because it relates to something we will, in a way, relates in a way to something we will deal with later on. Okay, so that was everything I wanted to mention to you, and so I'll see you next time, and thank you for watching. Bye.